Alright, so in this video, we're going to learn about L'Hopital's rule. L'Hopital's rule, again spelled like this. Again, we use this is more of the French spelling, but L'Hopital's rule is something that we can use when we're trying to find limits. So we know whenever we're trying to find a limit, we always begin by trying out direct substitution. So if we're given a limit, let's say the limit, let's get rid of this. Say the limit as x approaches 2 of 3x minus 5 over 2x. For example, we can use direct substitution, right? We get 6 minus 5, or I'll just writing it out. We get direct, if you use direct substitution, we get 6 minus 5, which is 1, over 2 times 2 is 4. So we can use direct substitution and get the limit. But in some cases, if we try to find a limit, we get an indeterminate form. If you can remember, back when we were doing limits, you can see, for example, if we have some function, limit as x approaches 2 of x squared minus 7x plus 10, for instance, over x minus 2. If we have something like this and we try to use direct substitution, you see that we get 2 squared minus 7 times 2 plus 10 over 2 minus 2. The numerator is obviously, if the denominator is obviously 0, 4 minus 14 plus 10 is also 0. So we get this indeterminate form. And we don't really know what to do, moving from there. But actually, if we get something like this, a 0 over 0, or in some cases we may even get infinity over infinity. So if we get something like, by using direct substitution, we get 0 over 0, or infinity over infinity, we can use L'Hopital's rule. And what L'Hopital's rule is basically doing is we're saying if we have the limit as x approaches some value of a, and we have our numerator, some n of x, and our denominator d of x. I'm just writing of x because we would need to eventually plug this in. But basically what we're saying is if we have some function, we would basically, if we have some limit where we're using direct substitution and get this indeterminate form, if we take the derivative of our numerator and plug in our a value, and take the derivative of our denominator, we can then try direct substitution, right? So we can then plug again this a back in, and we will get our limit. So in our original example that we just we had over here, and we were trying to find the limit as x approaches 2 of our function x squared minus 7x plus 10 over x minus 2. So this gave us an indeterminate form with direct substitution. So using L'Hopital's rule, we take the derivative of the numerator, which is 2x minus 7, and the derivative of the denominator is just 1. And so now we can try to use direct substitution. Using direct substitution gives us 2 times 2 minus 7, or an answer of negative 3. And this here is our limit. Right, now let's look at a couple more examples. So let's say we're trying to find the limit as x approaches 0 of sine of 4x over x. So here again, if we try to use direct substitution, sine of 4 times 0 is sine of 0, sine of 0 is 0, and we get our indeterminate form. So now let's try to use L'Hopital's rule. Using L'Hopital's rule, remember we take the derivative of the numerator, which is cosine of 4x times 4, because of chain rule, divided by the derivative of our denominator, which is just 1. Plugging in now, again, or trying to use direct substitution now, gives us the cosine of 0 times 4. Cosine of 0 is 1. 1 times 4 divided by 1 gives us a limit of 4. So there's our answer. Okay, let's look at a couple more examples of L'Hopital's rule, because we see it's clearly very helpful. So this one you'll notice is slightly more complicated than the first, in that, well, actually we'll see why. So you can see if we're trying to take the limit as x approaches 0 of 1 minus cosine x over x squared. If we were to use direct substitution, we get 1 minus 1 over 0 squared This gives us our indeterminate form, so we know we have to use L'Hopital's rule. So taking the derivative of our numerator, the derivative of 1 is 0, 0 minus, the derivative of cosine x is negative sine x, and the derivative of our denominator is just 2x. So this gives us sine x over 2x. And if we try to now see if we use direct substitution, you'll see that we once again get 0 over 0. So we have the indeterminate form again. So what do? Well, we apply L'Hopital's rule again. So we take the derivative of this numerator and this denominator once again. So the derivative now of sine x, right? So writing this out again, limit as x approaches 0 of sine x over 2x. L'Hopital's rule once again gives us cosine x over 2. So now, if we use our direct substitution, you see that we get an answer of 1/2. So if you see using L'Hopital's rule does not yield an answer, try to use it again. Use it until you're able to use direct substitution for your limit and get an answer. Alright, now let's see. We're trying to find the limit. Limit x approaches -1 of x to the 4th minus 1 over x plus 1. Clearly here, if we use direct substitution, we get an indeterminate form, so we have to use L'Hopital's rule. Taking the derivative of our numerator gives us 4x cubed, and of our denominator just gives us 1. So here, if we just use direct substitution, you can see we get an answer of 4 times -1 cubed over 1, which is just -4. So this is our answer here. Nothing too complicated. Alright. Now, try to pause the video again and try to solve this one on your own. Try to find the limit as x approaches 0 of 5x minus 2x cubed over 3x minus 7x squared. So, I assume you paused the video and gave it a shot, so now let's try to go through it together. Using direct substitution, you see that we get 5 times 0 minus 2 times 0 cubed, which gives us 0 in the numerator, and 3 times 0 minus 7 times 0 squared. So our indeterminate form is present here, so we use L'Hopital's rule. Taking the derivative of our numerator gives us 5 minus 6x squared, and of our denominator gives us 3 minus 14x. If we use direct substitution, we get 5 minus 6 times 0 squared over 3 minus 14 times 0, giving us an answer of 5/3. So our limit here is 5/3. Now, because we did mention it, let's try to look at one example where we see we get a limit of infinity over infinity, so we can use L'Hopital's rule. So let's say we're trying to find the limit as x approaches infinity of 2x squared over e to the 2x. So here, if we use a direct substitution, we get 2x to the infinity divided by e to the 2 times infinity. So this gives us then an answer of infinity over infinity, which is indeterminate. And so we would have to use our L'Hopital's rule. So if we take the derivative of our numerator, we get 4x, right? And the derivative of our denominator would simply be 4e to the 2x. If you remember back to our different special derivatives, 4 times e to the 2x. So, sorry, 1 second. There, I was getting a bit ahead of myself, obviously. Hopefully you did catch my mistake, that this is obviously not the derivative. It is just chain rule here, so we just get 2e to the 2x. So you'll see that if we then use direct substitution, we would get 4 times infinity over 2 times e to the 2 times infinity. So again, this is infinity over infinity. So, like before, we would end up having to use L'Hopital's rule once again. So, doing L'Hopital's rule once again, we have to take now the derivative. So if we're given the limit as x approaches infinity, we can rewrite this as the limit as x approaches infinity of 4x times 2e to the 2x. So here we use L'Hopital's rule once again, giving us 4 over, now we get 4 times e to the 2x. So now we will end up getting 4 over 4 times e to the 2 times infinity. Since our since our denominator would yield a very, very large number, which we're dividing a constant by, we end up getting an answer of 0. So then this would be our limit. So that brings us to the end of this video. You can see how L'Hopital's rule allows us to solve limits that we otherwise would have trouble doing so. So it's important that you know how to use this, but luckily it isn't too complicated. So if you did find this video helpful, please show your support by liking and subscribing, and leave in the comments any questions you may have, and suggestions for future videos. And I'll see you in the next one.